very much. So, good afternoon, everybody, and welcome to my talk. It's a real pleasure to be here. It's my first time at GOTO Copenhagen. I'm really chuffed to be here. My name is Mark West. I'm going to be telling you today about how I built a smart security camera using basically one of these little things. It's a Raspberry Pi, and a little bit of Java, and a little bit of Amazon Web Services. But to get started with, because I've never been here before, I thought I might say a little bit about who I am, and this won't take long. But basically, I'm an IoT hobbyist, surprise, surprise. I use a lot of my time messing around with hardware and messing around with software to have fun, basically. Build things like this. This is the first thing I built, a voice-controlled rover that was driven by JavaScript. I really kind of tried to make things difficult for myself there. So I've been working with this stuff for a few years now, but in my big job, the job that pays for the food on the table and puts clothes on the kids' backs, that's Bouvet. Which is a company in Oslo, Norway. So I'm an Englishman, but I've been living in Norway for about, most of my adult life. And in my spare time, I'm actually the leader of the Norwegian Java user group called Java Bin, and we arrange a little conference called Java Zone in Oslo. So if you're ever in Oslo in September, you should check it out. But anyway, what am I talking about today? Well, I'll split my talk up into 5 sections. And we'll start by talking about why I built this camera, why I had this project. And it was a project. It was a hobby project, but it was a real project with a project manager, my wife, and she's going to play a bit of a role in the story. I'm then going to talk about the first version of the camera, which is a very, very simple web camera. It's like a 101 project if you have a Raspberry Pi. And I'm going to talk about adding like smart image analysis to it with Amazon Web Services. So basically adding AI through the cloud. And then I'll talk about what I learned and how the cameras are. I have actually 10 of these cameras in production today. And then finally, this is new for this time. I've never done this before. I'm going to talk about actually adding AI directly to the Raspberry Pi by using a little chip, which I'm going to show you at the end of the talk. But then again, anyway, why did I build this camera? What was my motivation? And I had motivation, I had requirements, and I had a lot of input from my wife. And our motivation was that people have been breaking into the houses around us. So we have security in our house, but we have nothing monitoring our garden. So we wanted an early warning system that would tell us if somebody was in our garden doing stuff they shouldn't be doing. So my wife and I sat down. My wife works with ETIL. I don't know if you know, or ITIL actually in English. It's like basically bureaucracy for programmers. And I'm a programmer. So you can imagine the dynamic in our house. And we came up with some functional requirements for the project. We would monitor activity in the garden. We would send a warning when activity was detected and have a live video stream. So basically a motion-activated webcam, right? On a non-functional side, this is where my wife had a few things to say. Get it done quickly. Get it done cheaply. And actually make it portable so it can be moved around. Now, this isn't unlike a lot of projects we work with. Your boss comes to you, the pointy-headed boss comes to you and says, get it done quick, get it done cheap. So, in this project especially, I had a lot of constraints upon me on how much time I could use on this. So I decided to build the most simple motion-activated camera I could come up with. And basically, as I mentioned before, I was going to base it on one of these. This is a Raspberry Pi Zero-W. And it means it's like a very small Linux PC, very constrained device, not a lot of power, but it does have Wi-Fi on board. And the shopping list for to make the camera is basically you need a Raspberry Pi Zero, you need a power supply, you need an SD card. But the Raspberry Pi Zero has very small ports, so if you want to connect it to things like your TV or to USB peripherals, you're going to need adapters. So, I did a bit of searching around I had all this equipment lying around my house, but if you wanted to buy the stuff that I used, you might want to get yourself an essentials kit, which costs around about 250 Danish kroner, according to, a quick Google and a bit of quick currency conversion. Camera-wise, you could use a USB camera, but I chose to use a camera module, a Raspberry Pi camera module. They're tiny little things, and they come in 2 flavors. They come in the basic flavor, the green one, which is just a normal camera, and the black one, which is actually called the Pi Noir. And what's cool about this black one is if you pair it together with an infrared camera, an infrared light source, you get a night camera, a night vision camera. So that's kind of cool. Because the Pi Zero has small adapter or small ports on it, you need a camera adapter to connect the camera, a special camera adapter to connect the camera to the Raspberry Pi Zero. And then you're going to need to mount it all together and put it on your window. And for this, I used a Zero View, which is a piece of plastic with two suckers. So you mount your camera, you mount all of your camera and your Pi Zero on it, and you just stick it to the window. So total cost is around about 555 Danish kroner. Your mileage will vary. You can buy these individual parts cheaper if you get, just the basics. And if you have a USB camera lying around at home, you could use that. But this is just to give you an idea of the hardware cost. And this is what it looks like mounted together. And just to give you an idea of scale, that's the actual Raspberry Pi mounted on the back. So you see the SD card. On the front, you can see the camera poking through and the two suckers. So you stick it to the inside of your window looking out. And then you don't have to put it outside the house. You don't have to worry about weatherproofing it or finding, an outside power source for it. So that's the camera. That took me 15 minutes to put together. That was quick. But I needed software. And I decided to go for something basically off the shelf. And I went for something called Motion. Has anybody here played around with Motion? There's a few people. Yeah, Motion rocks. Motion rocks. It's great stuff. It's basically open source motion detection software. And it gives you excellent performance on the Pi. So you just download it and run it, and that's it. It also has a built-in web server for streaming video. So it solves that problem as well. And how it works, it looks for activity in your video. And when it finds activity, it triggers an event. And then you can actually wire that event to whatever you want to. So if you want to wire it up to a bash script to send you an email saying someone's in your garden, there you go, very, very simple. So it's about configuration. You only do the coding of the bash script, but the actual motion package, you're just basically configuring it. And just to show you very, very quickly, I'm not going to, there's not a demo, it's a webcam, so there's not a lot to demo. But if I just show you the live stream from my house. I hope my wife's got her clothes on. Yeah, no, she has. This is our garden. So that's our boring patio. And ladies and gentlemen, a web camera. It's not very exciting, but there are certain things here that are of interest that might be nice to note. That you can actually, you can have your date and time stamp here. You can actually give it a unique name. And in the top corner, if I can move up here, you see a number. And I'll explain what that number is in a minute. But that is just basically it. That's Motion. It also has the possibility of going to the console for the camera. And it's all hidden behind a security by obscurity, basic authentication, what could go wrong. But yeah, you have all of the parameters, and you can go in and set them online. So that's basically Motion. It's very, very simple. So let me see. Go back to the presentation. There we go. So how Motion works is it's basically just looking at all the images coming in from your video stream. A video is just a sequential list of images. So Motion is just comparing each image against the previous one. So in this case, images 1 and 2, exactly the same. But from image 2 to 3, something's changed, and Motion will raise an alert. And Motion only cares about the amount of pixels that change in an image. That's how it decides whether there's activity. And you can set the threshold of how many pixels have to change for Motion to trigger an event. So this is an example of the email, a dodgy man in my garden. Really, really simple stuff. Motion's really helpful, draws a nice little red box around the area where the pixels have changed. And you see in this example, there you go, that's the amount of pixels that changed from the previous picture to this one. So that's it. That was the first version of the camera. And it was working, really, really well. My wife went on holiday for a month with our kids, and we got warnings every time somebody came in the garden. This was the summer, and it worked really, really well. So to evaluate the project requirements, we monitor activity in the garden. We get a warning when something came into our garden. We have a live video stream that we can check when we get a warning. It was in place it took me a day. It took me 8 hours. 15 minutes to screw things together, and then a lot of time to download Raspberry and get it onto my SD card, and then a bit of time to download Motion and get that configured right the way I wanted to, and to create my bash script. But yeah, no more than 8 hours. So it's done quickly. The cost is relatively low, one-time cost for hardware, and it's portable. So brilliant. Happy wife, happy life. Everything was going well. Until the false alarm started coming in. So we have a lot of cats living in our area, and our cats love to use our garden. I don't know why it's our garden, but they like to use our garden to relieve themselves, go to the bathroom, to do other things that cats do to make little baby cats, all that kind of stuff. We have, obviously, clouds moving across the sky, and like the wind is blowing the trees backwards and forwards. My wife hangs out clothes in the garden, they get blown around. All of these things create motion. All of these things result in me getting an email. When it rains, rain drops down in front of the camera, I get an email. I was getting 250 emails a day. Yes. So you can imagine, what do? You just pipe it all to your junk mail and start ignoring it. And it was a nice project, it was fun, but at the end, it was a failure. And the problem is this: Motion only cares about the pixels that changed and not why. Motion is an idiot savant, basically. It's just looking for one thing, and it's not, there's nothing more to it. So my next step was to add some kind of smart analysis to the camera. And basically what I wanted was this, a filter. I wanted to keep motion, and I wanted to have motion running as it does today, but I wanted to have a filter between motion and the email. So saying, okay, there's a person in this picture, send an email, or there is no person, don't send an email. So I went to my project manager, like we all do, and I said, I want to make a change. I have a change request, and I want to send warning. Instead of sending warning when activity is detected, I want to send warning when human activity is detected. And my wife isn't stupid. She goes, how long would that take? And I was like, a week? I had no idea, right? So suddenly I was in the situation where I'd committed myself to a deadline that I wasn't sure whether I was going to be able to meet. How often do we experience that, right? So I didn't have a lot of time, and I scratched my bald head, and I thought for a while, and I thought about lots of different things, maybe using facial detection, which wouldn't work if they've got a mask on, or maybe building a neural network, which would take too much time. And then I saw this tweet, and this is 2 years ago. This is from Aaron Gupta. He was at the Amazon reInvent conference, and they just launched some new machine learning services, including image recognition. And I followed this rabbit hole, and it led me to working with Amazon. And actually what I ended up using was something called AWS Rekognition. Now, I want to make it very clear that I use a lot of Amazon products in my day job, but I'm not working for them. So you could do the same as what I've done with Google Cloud Platform, Microsoft Azure, you name it. It's just that I landed on Amazon first that led me to that. So Rekognition, it's a part of the AWS suite of cloud products, and it gives you image analysis as a service with lots of different APIs. So you can do face detection, you can do object detection, celebrity detection, I think they have, and it works both with still pictures and video. And it's all built upon deep neural networks. So Amazon somewhere have this big neural network which does all of their image analysis for them. And as I mentioned before, there are plenty of alternatives. You don't have to use Amazon if you don't want to. So just to show you how I use Rekognition, a quick demo of it. So I'm going to go to the browser again and to Amazon's, let me see, there we go, Rekognition console. So if I upload a picture, I'm going to upload a random picture. I'm going to upload the picture of this burglar. It gets uploaded and analyzing, and bang, there's my results. So what we can see from this picture, we can see that we don't have to be frightened of artificial intelligence yet, right? Unless you're a doctor or a burglar. No, but yeah, it's pretty certain this is a person. That's not bad. It thinks it might be a doctor. It's not perfect. Actually, Rekognition has got a lot better. When I first started doing this talk, it would come up selfie because it's holding a selfie stick. So Rekognition is getting smarter. I just want to show you another picture though, just to show that it's not perfect. And the picture I want to show you is this one here. Now at first sight, this looks like it processes well. You see person, human, baby, and I'm thinking, oh baby, it's probably thinking my son sitting in the corner of the picture, maybe it thinks he's a baby. And then I mouse over myself and I realize that I'm the baby. There you go, what can you do, right? Okay, right, so that's Rekognition. So you can see how I could use it, right? I mean, it's basically just to use that as a filter. I can send all my pictures to Rekognition, and then I can find out if they contain people or not. But the question is how I do it. And how I chose to do it in the end was not to have just an API call to Rekognition directly from the camera. I decided not to do that. And there's lots of reasons not to do that. There's good engineering reasons not to do that, kind of like single responsibility, a separation of concerns, but also just let the camera be a camera. I mean, it's a Raspberry Pi. It's not got a lot of power. Don't have it waiting for callbacks from like some kind of cloud service. So I decided instead that I would keep the camera as it was with motion, and instead of sending an email when a picture was generated, it would actually pass the picture on to Amazon or the Amazon cloud. And Amazon would then analyze the snapshot using Rekognition and send me an email if there was a person in there. And I didn't realize at the time, but actually I was building a data pipeline. And when you're working with the Internet of Things, you need to think about that. If you have lots of gadgets out there, how are you going to gather the data? How are you going to process it? How are you going to store it? Is it going to be scalable? If you add loads of extra endpoints, is everything going to scale as you want it to without you having to write things from scratch? But so I built this pipeline. And I want to go in a little bit more detail about what the pipeline contains. So it works, it's a few different AWS services working together. And what happens is imagine the camera generates a picture because there's motion in my garden. The picture gets uploaded to S3, which is Amazon's storage facility. That triggers something, an upload trigger, which in turn calls a workflow. And then the workflow calls Rekognition, and then finally, if the picture contains a person, sends me an email. So I'm using AWS S3, AWS Step Functions, Rekognition, and the simple email service. And I'm also using identity access management because all of these different components are different places in the cloud, and you need to make sure that components only call the components they're allowed to call. In addition to all of this, I'm using Lambda Functions to implement all of these, all the bits with, all of the sections with red around them now. They're all kind of like units of code or microservices, if you will. Everyone's heard of Amazon Lambda Functions, right? Yeah? I mean, like Lambda Functions, they're beginning to become more known and popular now. Google have their own functions and Microsoft as well. Lambda Functions are basically units of code. They're microservices, and you can write them using whatever you want to, Java, C#, Go, Python, Node, whatever. And they're serverless. We all know what serverless is, right? I mean, basically it means that your code is running on somebody else's server. That's what it means. I mean, like, let's not hedge it there. I mean, serverless is basically about you not having to worry about server uptime or managing the server yourself. Somebody else does it for you. That's serverless. So, as with all Amazon or cloud services, they're highly available. Lambda Functions are highly available and highly scalable. And you have a pay-as-you-go model, so you only pay for what you use. So you pay for each new invocation, and then you pay for how much time the function runs for, basically how many CPU cycles the function runs for. And you get loads of free usage with Lambda Functions. I think 3.2 million seconds a month if you go for the basic memory allowance. And the other thing with Lambda Functions is they give you access to all of the other AWS services through the SDK. So Lambda demo, I'm not going to give you a Lambda demo, but I'm just going to show you what a Lambda function looks like, what the code looks like. If I go, because basically I'm a Java developer, I'm a Java developer. So I originally wrote the camera in Node. So all my microservices are written in Node.js, but now I decided to, I wanted more boilerplate, so I went for Java. So basically, if I just zoom out here, you can see the code there. You don't have to read the code, but like this is a Lambda function. This Lambda function does one thing. It takes in a picture, sends it to Rekognition, gets the output from Rekognition, and then pushes the output back out the other end of the Lambda function. So this is basically a proxy for Rekognition. And what it's doing is, if we just zoom in a little bit, it's taking in two objects. It's taking the parameters object, which I've created. That's a POJO, which just contains a load of information, which I'll show you in a second. And the context. The context object is something which is generated by Amazon itself, and it contains like a logger. It contains information about which function you're running and where it's running, that kind of stuff. And basically, the parameters function, or parameters object, is just a POJO with contains information about the location or the name of the snapshot, the location of the snapshot, whether an email should be sent, a list of the labels from Rekognition, and finally, it contains information about where the images are archived, because I archive all of my images in S3 after they've been processed. So that's basically the parameters object. It's just getters and setters. and parameters. And this Lambda function, all it does is it starts off, it logs the input, it creates a recognition client, it creates a recognition request using the information from the parameters object, it calls recognition, and then finally it takes the output from recognition, puts it back in the parameters object, logs it, and then returns it. Simple stuff. And basically, if we look at the Lambda function console, very briefly, so let me see, here we go here, just zoom in here. So if you go into the Lambda function console, you get a list of all your Lambda functions, and if I just list the ones that I want, the Java ones, these are all the Lambda functions that I use, the Java Lambda functions that I use in my camera. And the first one here is the one I just showed you, Recognition Image Assessment Java. And if you click on it, it's a bit of a noisy interface. So I think Amazon are trying to make it better, but at the moment I think it's a bit too noisy. But the most important things here are actually the basic settings. And it's here, which you can see this, it's here where you can allocate how much memory you want the Lambda function to have. And a little tip, if you're going to be using Java in Lambda functions, it's often best to turn up the memory a little bit. Because like when Java Lambda functions, when they spin up, when they instantiate themselves, they use a bit of memory to get started. And I found that if I use 128 megabytes, which is the lowest memory setting, then I get out of memory errors. So I set it to 256, never have a problem. You can also set your timeout here. How long do you want your Lambda function to run if it starts looping? How long do you want it to loop before it gets closed down? And you can have it up to 15 minutes, which is a bit dangerous, because if you're using a lot of memory and it starts looping, you can quickly owe a lot of money to Jeff Bezos. And you don't want to owe money to Jeff Bezos, I can promise you that. So, but that's basically Lambda functions. Very, very, very simple. Step functions, on the other hand, well, they're not complicated, but like they're a bit different from Lambda functions, because step functions are about orchestrating your Lambda functions into workflows. So if you imagine your Lambda functions like microservices, step functions are orchestration. And so step functions, you can actually make state machines or workflows. You can define them using JSON files. So you write a JSON file with your steps and the transitions between those steps. And one thing to remember with step functions, you pay for each transition, right? So if you have two step functions and one has 5 transitions and the other has 10 transitions, you're going to pay double as much for the one that has 10 transitions. It seems obvious, but some people think they pay for each step function invocation, and then they get a shock when the bills come in. But yeah, step functions are the same as Lambda, highly available, serverless, scalable, and whatnot. This is what the step function looks like for my camera. And it's pretty obvious if you run through it, but I'm just going to step through it and just explain what it's doing. So the picture is uploaded to S3, and then this step function is triggered. So the first thing that happens is the Lambda function I just showed you, the Java one, takes the image and sends it to Rekognition, or sends a reference to your image to Rekognition, takes the results from Rekognition and puts them in the parameters object and then sends it out. That parameters object is then picked up by the next Java Lambda function, which is about evaluating the results, or evaluating the labels that you got back from Rekognition. So it compares the labels against the whitelist that I've created, and if it finds a match, then it sets the alert flag in the parameters to true, and outputs the parameters object. The next step is not a Lambda function call, but a step in my step function, which just looks at the contents of the alert, send alerts flag. If it's set to true, another Java Lambda function is called to send me an email, and then finally another Java Lambda function is called to archive the image. And it's simple as that. And of course we have an error handler because I'm a good programmer and I want to make sure errors are handled properly. So that is basically it. So now I want to give you a quick demo of the data pipeline in action. I have 2 pictures here, which are in many ways identical, apart from the big bald Englishman in one of them. And what I'm going to do is I'm going to upload both these pictures of the data pipeline and show you how they're handled differently. So if I just go back to my desktop. So these are the 2 pictures. Now if I just go to my Finder here, I think I had it. So here are the 2 pictures. This one with a picture of me in it is called test positive, and the other one is called test negative, obviously. And if I just upload those quickly using the command line, so I'll upload the test positive one first. I'll need a password, here we go. See if I can remember that. Oh, it's a long password. Please. Yes. Okay, and then also upload the test negative. So both pictures have been uploaded to S3. So what's happening now is S3, or the trigger on S3 has been triggered. It's called the step function, and the step function is processing both images. Now, if I go back to the Amazon console, and I'll go to the step function console, and click on this one here, we can see I've got two step functions running. So if I just open those both up in a new tab, and we can look at each one of them. So we'll take the first one. This is the first one. And, oh, it's still running. There you go. That's exciting. That doesn't happen very often. And it's still running. Yeah, it's sending an email. Okay. So this step function here is the one that got the picture of me, I think. So if we look, what you can do with this interface here, you can actually see the input and output to each step in the step function, actually do your debugging. So it's still running. So while that's still running, let me just check the other one and see if that's finished. That's still running as well. That's very slow. Must be something going on in the Amazon world. Okay, so this step function is finished now. So this is the one. If we click on the first step, we can see which picture was sent into it by looking at the input. Let me just do that. There we go. Can you all see that? Yeah, okay. So if I click on the input, we can see the input that came in was the test negative picture. You can see send alert is set to false so far. And if we see the output from this first step, which called recognition, we can see we've got some labels. We've got door, sliding door, chair, and furniture. So the next step then evaluates the labels. So it takes those labels in, and the output from that is the send alert is still set to false because it defined a person, because you've got door, sliding door, chair, furniture, there's no people there. And then the make alert decision, that's not a call to Lambda function, it just checks this value here, send alert, sees it's set to false, and then just goes straight to archiving the image. That's it. If I go to the other step function instance, we can see that in this case, the picture that came in was the test positive picture, and the output from recognition was person, human face, home decor, man, and beard. Quite happy with that last one, beard. It used to say goggles. I don't know why. I think it was because I was really tired. So dark circles around my eyes. But why it said goggles, not glasses, I don't know. Yeah, so anyway, it actually, in this case, it returns like values, which are interesting. So the next step, it takes those labels in, and then the output here, it's actually set send alert to true, resulting in sending an email and archiving the picture. So that's basically it. Now, if I finally go to Gmail, hopefully I've got a picture. Or an email, should I say. And there's the email. And yes, it looks safe. Google doesn't like my camera. Right, so we see here, there's that picture of me, and we see the labels. So that's basically how it works. It's pretty simple stuff. Yeah. But what's good about it is it's very, very, scalable. Because you can connect as many cameras as you want to this data pipeline without any problems. So, evaluation. What have we learned? Well, this comes up a lot. And yes, it has. Not at my house or any of the 10 cameras that I've got installed, but like when I first created this project, it was when when Rekognition was a relatively new service, and something happened, and for some reason it got picked up. My project got picked up by Hacker News, and then suddenly it exploded, and people started implementing the same camera as me, using the same recipe as me around the world. And I've had 2 people contact me to say that it's caught criminals. There's one guy in California, a student, and he was just like at home, no, he was at university one day at a lecture, and he got an email, and there was a person trying to get into his patio door. So he sent the real-time streaming video link to the police, and they actually managed to get to his house and capture the guy before the guy that actually stole anything. That's pretty cool. Another example was somebody who thought somebody was trying to steal his car, and then they got proof that somebody was coming around and trying the doors every night and that kind of thing. So it has worked in the real world. At this point in time, as I say, I have quite a few cameras running, on and off. It's a seasonal thing because my in-laws have a few different huts in Norway, down by the water and in the mountains. So they have different cameras running there when they're not there, for example. So I think we have about 10 cameras running, and it seems to work pretty well. The cost for 4 cameras, I had 4 cameras in October running, and they generated 18,496 images. And the total cost was $27 American, which is actually quite high. But if you remember, that's 4 cameras. But also, another thing to remember, if your garden or your use case generates a lot of pictures, then your cost is going to go up, right? But what's interesting is when you split your costs by service. So we can see here that, step functions, not really costing you an awful lot of money. The use of S3 for storage, not costing a lot of money. Simple email service, not costing a lot of money. Lambda doesn't cost a penny. I'm nowhere near breaking the free tier for Lambda. But Rekognition, that's where the money goes. The first 12 months of using Rekognition, you get 5,000 pictures a month for free. But after that, you have to pay for everything. And the cost is around about $1 per 1,000 images. So it's very important to remember that if you're going to do something like this, that the cost initially will be lower. And if you have like a garden or a use case that generates a lot of pictures, your costs will therefore rise. So if I look at the project requirements, I'm pretty happy, actually. I think that I managed to solve all the things I wanted to. The cost is definitely something you can argue about, and it's something that I've become less and less happy with over time. It's, a small dollar amount every month isn't a problem until you've been paying it for a few years, and then you start to see that cost builds up. But overall, I'm happy with how the camera's performed. There are negatives and positives. On the positive side, the camera's reduced the amount of false positives that I used to get. And as I mentioned before, the AWS pipeline gives me a really, really flexible and scalable solution. So I can connect as many cameras as I want to without having to change a line of code. It didn't cost me much to get started up and experiment because you get a lot of cheap stuff from Amazon the first year. And all my project requirements are satisfied. On the downside, the monthly cost grows after the first year. And over time, that cost builds and builds and builds, right? If you pay $20, $30 every month for a year, it quickly becomes to be a large amount. The other thing about Rekognition, it doesn't like noisy environments. If you have a lot going on in your garden, I think Rekognition struggles sometimes to find all of the labels for all the objects in your garden, especially the people. So if I have an example of my girl sitting on a rock in the woods in Norway, and the naked eye, you can see her straight away, but Rekognition can't see her. Google Vision can't see her. Microsoft Vision can't see her. So all of these, AI as a service, image processing service, they're not perfect yet. The other thing about Rekognition is a black box. You don't know what it's been trained on. You don't know what it's optimized for. And depending on your use case, Rekognition won't work. If you want a camera that tells you if a deer or an animal comes into your garden, then Rekognition might not be the right solution. And the biggest problem is the results from Rekognition are only as good as the pictures you upload for Motion. And just to explain that, Motion has a strategy for uploading pictures or for generating snapshots from the video. When it detects activity, it sets up an event with a start and end and a timeline. And that timeline will have multiple pictures. The question is, which of these pictures should Motion upload? Should it upload the first picture? Well, that's okay, but if it's just the tip of my toe coming into frame, that's not going to be good enough for Rekognition to find me. What about the picture with the most central activity? Well, that's okay unless I'm ducking behind something in the center of the screen. What about the picture with the most pixels change? Well, yeah, if I'm putting my hand over the camera, right? Or maybe I should just upload all of them. But that's going to cost a fortune. And that's the problem with my solution as it is today. You're going to have to make a decision between hit rate and cost. One snapshot, lower cost, lower hit rate. All the snapshots, higher cost, higher hit rate. So that's where we are with the camera. So I want to talk a little bit now about what I've been doing recently. I think, around about 3 or 4 months ago, I started looking at other alternatives to solve this problem with the camera because I started getting annoyed with having to pay Amazon. And I started looking about how I can have AI running on the actual edge device itself because you can have it running in the cloud like I'm doing today, but you can also have it running locally. And one of the things I tried was OpenCV. OpenCV from 3.2 onwards has support for deep learning neural networks. So you can actually plug it into OpenCV and do your inference in OpenCV. But on the Raspberry Pi Zero, you can just forget it. It's not going to give you any performance at all. On the Raspberry Pi 3, 3B+, I think you get maybe 1 frame every 2 seconds, which is, it can be okay, but it's really pushing things then. So I started looking at different ways of bringing AI to the edge. And as Morpheus would say, what if I told you that you can actually have that? You can have fast AI-powered image processing on the Pi. You actually can, if you're willing to buy more hardware. Have any of you heard of the Intel Movidius neural compute stick? Yeah? There's one chap there? Excellent. This is a new piece of hardware that's been developed. Well, it's not new, it's about a year old now. It's been developed by Intel, and it's a USB stick. You just stick it into your Raspberry Pi, and there you go, deep learning inference. And you can look at it as an extra processing unit for your Raspberry Pi. It contains a VPU, and the VPU is the same chip. It's actually the same chip that you'll find in your DJI drone. If you have a DJI drone, and it can do follow you modes and stuff like that, it's powered by the same chip that's in here. And my thinking is maybe this can free the smart camera from AWS. The thing to remember here is that this is for deep learning inference. It's not for building deep learning models. So you're going to need to go out there, you need to find yourself a deep learning model of your own, build one of your own, or find one on GitHub or something. I've actually used the MobileNet single shot detector neural net, which is it's a pre-trained neural network, and it's trained to recognize 20 different objects like people, airplanes, sheep, and that kind of thing. So I decided to do an experiment with this Movidius, real-time video annotation, see if that would work. And this requires me to split my work between the Raspberry Pi and the Movidius. And this stuff happens automatically. It's nothing you have to do manually, but I just want to show you how this is working before I actually demo the experiment. And what's happening is the Pi is connected to a web camera, and the Pi is picking up a single frame from the video stream. It crops that frame and makes it ready for processing by the deep learning network. Because the thing is, when you train a neural network, you train it with images at a certain shape and size, and therefore, when you're going to test it with new data, you have to make sure the new data has the same size and shape and properties that your training data has. So the Pi will actually crop the picture, and then it forwards it onto the Movidius. And the Movidius uses the pre-trained neural network to find objects in the image, and then sends a response back to the Pi saying, okay, these are the objects I found, here are my confidence scores, and here are where the objects are located. The Pi then annotates the video, displays it in the desktop, and it just goes round and round like that. Now, I'm going to show you first, I'm going to show you a video, hopefully this will work. This is me, it looks like I'm going to take off or something, but like, this is me in my basement at home, trying the camera out for the first time. So it finds the sofa, it finds me, and this is a Raspberry Pi 3. So it's relatively quick. And it can find lots of different objects. It gives the boundary boxes, it gives the objects it finds, the confidence scores. I was showing off there. I was really happy when that worked. I was kind of, yes. And then I looked up another thing, another object. Bah. Took a little bit longer. There you are. I mean, and this is a Raspberry Pi with the Movidius. If you didn't have the Movidius, this would take a lot longer. And the bottleneck is actually on the Raspberry Pi as well. So I was getting about 4 or 5 frames a second out of this. So I tried different combinations of different types of Pis and different modes. I tried threading my code. I tried, tried out Pi cameras and USB cameras. And I got relatively good frame rate per second. I'm happy with all of those. I mean, like, on the Pi 0, yeah, you need to run it in headless mode. So then you won't get the video display, but you will get the videos annotated. So if they're sent to you in an email, that'll be completely fine. But as it stands now, we don't have the web video. We don't have the webcam, like Motion gave us. So we don't have the streaming video server that we can go and look at and see what's going on in the garden. But this is just an experiment to see if the Movidius could be used to replace AWS in my solution. What I want to do, if you don't mind, we could just try running. I've got a Raspberry Pi running on stage here. I just want to see what kind of it generates for you people who sit in the audience. It probably doesn't generate much. Now, I'm just going to point out that these pictures aren't saved anywhere. GDPR. So we have to be careful. I just have to make sure I can change to the right. I have to change to a local network here because, working on Raspberry Pis live can be a pain because you need to be on the right network. Let's see if I can go to my desktop. Now, this might run very, very slowly because the Raspberry Pi now is running of a remote desktop, and they don't often like that. But let's see if we get good results out of it. If I just go to the right directory. I'm just very interested in seeing how this works. It's low light anyway, so it might not do much. Just out of interest, really. And it might be that the actual video quality, the frames per second, is really bad. So we'll see. It doesn't find anything, because the light's too dark. But if I go and walk in front of the camera, there you go, person. That's not bad, is it, really? It doesn't see all you guys, but it doesn't matter, because I'm the one that matters. I'm the one that counts. Sorry, that was very egocentric. I do apologize. But you see how something like this can be a lot of fun to play with, and actually does have practical uses as well. Right, so, and if anybody wants to come and look at this at the end, we can just come up and have a look at the chip and everything. It's fine. So, to evaluate the Movidius then, the main benefit of Movidius is it processes every single frame, unlike AWS and Motion. With AWS and Motion, you need Motion there to be a throttle to make sure that every picture isn't processed by AWS. Otherwise, it would cost you a fortune. There are no ongoing costs with the Movidius NCS. And you can bring your own model. As long as it's Caffe or TensorFlow compatible, you can train your own model. Do what you want to do. So the Movidius is more adaptable to your use case. And Movidius, of course, makes things a lot faster than running the Raspberry Pi and OpenCV on their own. On the downside, the bottleneck is the Raspberry Pi. Movidius, I checked the Movidius to see how quickly it does the inference, and I think it's around about 100 milliseconds per picture, 90 milliseconds per picture to do the inference. So the bottleneck is the Raspberry Pi having to annotate the images and mess around with the image I/O. With the Movidius, you don't have the data pipeline. Now, you could build one, but out of the box, you don't get the data pipeline that you get with AWS. So, and therefore, you might have to buy lots of Movidiuses, which might add up, might increase your costs. And finally, the future for the Movidius NCS is a bit shaky, I think. See, the people behind it are really great, and the forms are really great, but I've struggled a lot getting the software working. And they've done things like take down the GitHub suddenly without any warning, and it just seems to me that Intel don't really have a very good strategy for making the Movidius successful. Or maybe the Movidius is just a side project to them and not a revenue stream, so they don't want to prioritize it. So I'm not sure whether the Movidius will be around for that much longer. But luckily, Google have announced the Google Edge TPU accelerator. They announced this all the way back in the summer. And it's basically the same thing. And it's supported by the AIY guys who do all of the IoT projects for Google. So I think the support for this is going to be pretty good. The only thing is it was supposed to come out in the autumn, so they'd better hurry up. It hasn't come out yet. But yeah, definitely something to look into, right? So the slides are going to be available from both the GOTO website and the app later on, I believe. And I'm going to make them available via Twitter, so I am going to put them onto SlideShare. So any of you who download the slides, these are all hyperlinks to my blogs and more information on what I've talked about today if you want to do some more reading. But they're hyperlinks, so you don't have the web address here, of course. And other than that, I'd just like to say thank you so much for listening, and don't forget to vote. Thank you very much.